So 2.6 is solving absolute value inequalities. You're going to see some similarities here from solving absolute value equations back in chapter 1 and solving compound inequalities, which is what we just did in 2.5. So an absolute value inequality here in the vocab is basically an inequality that contains an absolute value. An inequality that contains an absolute value. So an absolute value inequality is an inequality that contains an absolute value. We actually have two different types of absolute value inequalities, okay? And this is going to kind of relate to what we learned in 2.5 with compound inequalities. We could have and inequalities or inequalities, okay? We learned and or compound inequalities. And inequalities are going to come whenever our sign, the absolute value, is less than, which remember it looks like that, or less than or equal to. Which looks like this. So if it's less than or equal to, we know we're going to use the word and to write a compound inequality. If it's greater than or if it's greater than or equal to, then we're going to use or. So here's how I remember it. Less than is and, greater is or. So here's how I remember it. I'll say less than is and, greater is or. Less than is and, greater is or. So if we have an absolute value that is a less than, we're going to write an and inequality. Here's the reason we're going to write compound inequalities. If you remember back to chapter 1, when we solved absolute value equations, we wrote two new equations. We're going to do the same thing when we solve an absolute value inequality. We're going to write two new inequalities. Because this is a less than or equal to, less than is and, I'm going to put the word and in between my two new inequalities. So I'm going to write two new inequalities and is going to go in the middle. So my two inequalities, my first one will be x plus 7 less than or equal to 2. So it's basically the same inequality but without the absolute value. Now watch closely here. The second one, the x plus 7 doesn't change, but we have to switch the sign to greater than or equal to, the symbol to greater than or equal to and the sign to negative. So that's an important thing to note. When I write my second one here, I flip the inequality and switch the sign here, okay? Flip the inequality, switch the sign, now we have our 2. Now we can solve both of these separately. So here I can solve by doing minus 7. I'll get x is less than or equal to negative 5. And then I'll solve the other one, also subtracting 7. X is greater than or equal to negative 9. Okay, so basically what that means is x is between negative 9 and negative 5. So there's my inequality. X is between negative 9 and negative 5. Okay, I'm going to go ahead and put that on my graph. I'll have to start with negative 9 around here, and I'll count up. Make sure we include negative 5. I'll also count down here so we have everything labeled. All right, let's start at 9 because it's a smaller number. I need a closed circle at 9. And then I need a closed circle at negative 5. And because we're talking about an and inequality, we're talking about in between those two numbers, so we want to join those two circles. Let's try the next one. Similar idea here. I'm going to make my two new inequalities. Because this is a less than symbol, less than is and, I'm going to put an and in between my two new inequalities. My first one will be 2w minus 1 is less than 11. My second one will be 2w minus 1. Switch the inequality, greater than, flip the sign, negative 11. Okay? Again, I can go and solve both of these. So I'll solve the first one by adding 1. And I'll get 2w is less than 12. I can divide by 2. And I'll get w is less than 6. And I'll add 1 here. And I'll get 2w is greater than negative 10. I'll divide by 2 here and get w is greater than negative 5. So if I were to write this as a string of inequalities, I'll take my smaller number first, negative 5 is less than w, which is less than 6. There's my final answer. So let's go ahead and graph that. I think I'm going to have to start all the way down here with negative 5, and hopefully we have room to fit up to 6. Looks like I'm just going to add one more dash here so we can get to 6. I'll need open circles at both of those, and because it's an and inequality, we're joining those two inequalities like that. Let's take a look at the next one. You might notice that there's not a graph for the next one because something interesting is going to happen here. So this is saying that the absolute value of 8x minus 11 is less than 0. Think about what less than 0 means on a number line. Less than 0 means that it's negative, right? So when I say less than 0, that's basically saying it's negative. Well, we know something. We learned something back in chapter 1. We know that absolute value, make sure you write this down as a reminder, absolute values cannot be negative. So by saying less than 0, we're basically saying it's negative. Well, we can't have that, so it's no solution. So if you see an absolute value that's equal to a negative, you know it's no solution. If you see that it's less than 0, that's the same as saying negative. If you see less than negative 2, well, anything less than negative 2 is still negative, so that would be no solution. So anytime you have an absolute value that is equal to a negative, less than a negative, or less than 0 is automatically no solution. Okay? It can't be less than a negative. It can't be less than 0. Okay? Does that make sense? All right, let's go ahead and try some OR inequalities. So again, we have an absolute value inequality. Anytime I see absolute value, I'll start by making 2 new inequalities. Because this is a greater, or equal to, greater than or equal to is OR, so I'll put an OR in the middle, and I'll write my 2 inequalities. The first one is c minus 1 is greater than or equal to 5. The second one is c minus 1, flip the inequality, less than or equal to, switch the sign to be negative. And then I'll go ahead and solve both of these. So I'll add the 1, and I'll get c is greater than or equal to 6. Or, let's solve the other one, add the 1, c is less than or equal to negative 4. There's my solved compound inequality. I can graph that. I think if we start at negative 4, we should, if we count by ones, we should be able to make it. Let's see. Perfect. So I need greater than or equal to 6, less than or equal to negative 4. The arrows are going outward because it's an OR inequality. Let's try the same thing. Now on the next one, there's a few things that we have to worry about first, okay? So whenever we have absolute value, anytime I have absolute value, I know I have to make my 2 new equations, right? But in this case, before I do those 2 new equations, I have to get rid of this 4 and this plus 1 because I need the absolute value to be by itself. So I'm going to start by getting rid of the plus 1 by actually subtracting 1 on both sides. So I'll subtract 1 here, subtract 1 here. It cancels on the left side. I'll end up with 4 times the absolute value of 2x minus 5 is greater than 20. Then I have to get rid of the 4. I'll do that by dividing by 4 so that it cancels. And then I have to divide the 20 by 4 as well. So now I have the absolute value of 2x minus 5 is greater than 5. Now I can split it up and make my two inequalities. It's still a greater than symbol, so it's still an or inequality. My two inequalities are x minus 5 is greater than 5. 2x minus 5 is less than negative 5. Don't forget to flip the inequality and switch the sign. Flip the inequality, switch the sign. And then I can solve. I'll solve this by adding 5 to both sides. I'll get 2x is greater than 10. And then I'll divide by 2 on both sides, and I'll get x is greater than 5. Or, solve the other one, I'll still add the 5 to both sides. This time I get 2x is less than 0. That's fine, we can have 0. When I divide by 2, I get 0 divided by 2. That's just 0, so x is less than 0. So I was kind of running out of space, but there's my final answer. X is greater than 5, or x is less than 0. On a number line, I'll start with 0 here. 1, 2, 3, 4, 5. I'll keep going. Finish on the other side. And I'll put an open circle at 5 with an arrow to the right, an open circle at 0 with an arrow to the left. Remember, because it's an or problem, the arrows are pointing away from each other. We actually sometimes have a special case, another special case with inequalities. So let's take a look at the next ones. The next one says the absolute value of 10 minus m is greater than or equal to negative 2. We know that absolute values cannot be negative, right? Another way to say that absolute values can't be negative is to say that absolute values will always be positive. So absolute values cannot be negative, which means they'll always be positive. If something's always positive, think about greater than or equal to negative 2. If something is greater than or equal to a negative or greater than or equal to 0, it's always positive. So in this case, we don't have to do any solving. It's always going to be positive, which means my answer is IMS. Okay, so if it's always negative, then it's no solution. If it's positive, then it's IMS. Let's talk, the last thing we're going to talk about is absolute deviation. So there's kind of a little formula here for absolute deviation, and then we'll put that to use in example 3. So the absolute deviation is equal to the absolute value of x minus our given value. The absolute value of x minus our given value is the absolute deviation. So let's use this to solve example 3. Example 3 says you're buying a new computer. The table shows the prices of computers in a store advertisement. You're willing to pay the mean price, here we are with that word mean again, with an absolute deviation of at most 100. How many of the computers meet your conditions? So I underlined what I think are some important keywords here. Again, mean, we talked, mean is the average. We find it by adding all of them together and dividing by the total. So let's start by finding the mean. I'm going to find the mean by adding all these numbers together and then dividing by the total. So why don't you grab your calculator, open up a calculator, type 890 plus 650 plus 660. These are just all the prices of the computer. Plus 450, sorry. Plus 725 plus 750 plus 370 plus 670 plus 650 plus 825, and we'll divide all of that by the number of computers, which is 10. So first type all of that in, add it all together, and then divide it by 10. you should be getting, when you do that, 664. So the mean is 664. The average price is 664. So we are willing to pay the average price with an absolute deviation of at most 100, okay? So absolute deviation is going to be x minus our price, which is 664. At most is less than or equal to 100. So now we have our equation or our inequality. We can go ahead and solve this by making two new inequalities. X minus 664 is less than or equal to 100. Because it's less than or equal to, I should put an and in the middle. Less than is and. And then on the other side, I'll have x minus 664 is greater than or equal to negative 100. Don't forget to flip the inequality and switch the sign. And then I'll go ahead and solve this. I'll solve this by adding 664 to both sides. So I'll get x is less than or equal to 764. And here I'll do plus 664 on both sides as well. And I'll get x is greater than or equal to 564. So remember, and means in between. So basically this means I'm willing to pay between 564 and 764. So now let's look at the price of our computers. Which ones of these fit in that price range? I'm going to highlight them. 890 is too high, 650 is fine, 660 is fine, 450 is too low, 725 is in there, 750 is in there, 670 is in there, 650 is in there. So it looks like I've highlighted all the ones that will work for us. There are 6 computers that are in that range of how many we would actually buy. Our range of 564 to 764. So the key here with solving absolute value inequalities is making your two separate inequalities and then deciding, is it going to be and or based on your symbol. As a reminder, if it's less than or equal to, it's and. If it's greater than or equal to, it's or. So those are kind of your reminders of when you should use an and when you should use an or when we're talking about absolute value inequalities.